Okay, good morning. So let's continue with our subject, which today I want to talk about, or start talking about complex variables. A very sort of brief review of complex variables, because I want to show complex variables applied to PDE modeling. That's the idea. And sort of motivate to you that singular integral problem I showed last time, which applies to interface dynamics. So let me start with very basic complex variables, remind us of complex variables, analytic functions. I'll move quickly. There's more in the notes than I'll be talking about. And of course, it's taken from standard complex variables book. So let's think of the following. So if we have this complex valued function of a complex variable, okay, and of course we can define the derivative of the complex derivative of this function like this, right? So what we know, which is very, very nice and gives us many properties, is that, and as we'll see, the complex valued derivative leads us to Cauchy-Riemann equations. And I'm going to very quickly associate this, complex variables, to Laplace's equation, right? I mentioned this before. Real part and imaginary part of an analytic function is basically harmonic. So one interesting thing about this, let me do a little drawing. I have to pick and choose from my notes. Is that if I'm in the z-plane, this is x, this is y. If I'm taking the derivative, right, I can take the delta z in any direction, right? The derivative is when z approaches z naught. So therefore, from this, we will get the Cauchy-Riemann equations. Okay? So this derivative is defined for any direction. There's something which is very interesting. Let me write down, remind us, right? That if, let me write it, if exists, okay, in a neighborhood, let me abbreviate, of z naught, then f is analytic in that neighborhood. Okay, so this is a very nice thing about complex variables, right? If in an open neighborhood of a point, you have a converging Taylor series, super smooth function, infinitely many derivatives, it's analytic. That's something very nice. Okay, so let me skip here some properties, and let's see how we get the Cauchy-Riemann equations, which is a system of PDEs, right? From this very simple definition. So do you remember that? How does one get Cauchy-Riemann equations? And then I'll give you, since this is an applications course with PDEs and so on, I'll give you some fluid dynamics interpretation of all this, in particular of the Cauchy-Riemann equations. Okay? So it's very simple. You don't have to know fluids. You understand it. So look, if I can take this derivative in any direction, right, meaning you can approach z naught from any direction because it's a complex valued derivative, I can definitely choose two specialized directions. the x and the y direction. Okay? So if, let me put it like this, delta y is identically 0 in delta z, this means x direction, then I have this. Let me put it here. Let me try and make. Right, is equal to this, which is equal, now you see my notation. Let me see how I'm writing the notes. Okay, like this. Okay, so the notation speaks for itself. So f is defined as u plus I. V, real part of f, real imaginary part of f. Variables are x and y. Okay, and this is equal to, well, right, just u of x. Let's do it like this. V of x. Right, and then if we specialize to delta x identically 0, then delta z is I delta y, okay, and we get that df dz is minus I dy, which is then equal to minus I okay? So from this, right, we get the Cauchy-Riemann equations. So the Cauchy-Riemann equations tells us that ux is equal to vy, uy is equal to minus vx, where these are partial derivatives. Okay? Right, you just multiply, see, this guy is equal to this, blah, blah, blah. Right, if we have smoothness and all that. Okay, so this is the Cauchy-Riemann equations. And, of course, if this is smooth, I mean, if everything is okay, right, we can get that both are harmonic functions. That is, solve Laplace's equation, right? Differentiate this with x, differentiate this with y, you kill the v, and do the other thing the other way around. Okay? So, therefore, and this is where I'm going to get to. If I have a problem where my modeling deals with some sort of potential, that is, a function which the Laplacian is equal to 0, okay? Remember I mentioned to you water waves, I had the water wave potential, many problems. Now we're going to have the interface problem, and so and so. And the potential, as I'll show you, for those who don't know fluids, I'll give you a quick indication that potential usually we use when the fluid is considered incompressible and maybe rotational and so on. I'm going to get to that soon. I can then use complex variables because basically if I use a complex valued function here, I'm going to soon show to you a complex valued potential, I'm already satisfying Laplace's equation if I have a function that's analytic in some domain. So that's why it's interesting in 2D problems, because this is 2D, obviously. 2D problems, sometimes it's interesting, and interesting physically and interesting mathematically, you'll see soon, to use complex variables as our modeling tool, because we get a free ride on properties of complex valued functions. And as I mentioned to you, if the function is just analytic everywhere, it's boring. You know, the problem is not interesting, as you will see most of the time. Singularities are important, and as you will see, I'm going to put singularities into the problem. We're going to get a singular integral, and that's not only nice and cool mathematically, interesting mathematically, but it's also very interesting from the physical modeling. it simplifies things from the modeling to some extent, but complicates in another sense. We'll see that. Okay? So I just already mentioned that if a function is analytic, its real and imaginary parts are harmonic functions. Okay? And let's see, there's so many things here I have to pick and choose, is that, that's right. And V is said to be the harmonic conjugate of U, okay, which is the imaginary part, and so on. Okay, so this is a very quick, brief review of some aspects of complex variables. Now let's use this very brief, just basically terminology to some extent, in a fluid dynamics problem. Okay? So in a fluid dynamics problem, so now using complex variables in a fluid dynamics problem. So we usually in fluid problem, in particular that problem that I showed you last time, I will repeat it today. Let's consider our fluid and say our flow, right, to be incompressible and at first irrotational. Then I'll give up the hypothesis of irrotational at certain points. So for those who haven't seen fluids, right, people who are here in the room and are watching this, when we say the fluid is incompressible, it means that the first approximation, you can't quite squeeze it. You cannot change its density. Okay? That is okay, for example, for hydrodynamics. For example, water, liquids, and so on. Under certain hypotheses, depending on the problem, you can consider it's not compressible. So the density doesn't change. Right? It's more dense in some parts than other parts, and so on. Okay? With fluids, for example, if you're talking about underwater acoustics, an acoustic wave, it's a pressure wave. Then you have to consider the compressibility of the water. But if you're considering a tsunami, for example, a wave in the ocean, incompressibility is okay. All right? And irrotational means that there's no swirling to some extent. Okay? But the swirling can be also friction, shearing can also be considered a rotational aspect, as we will see today. So from the usual hypothesis is that if our flow is considered incompressible, the divergence of the velocity of field is 0. And if it's irrotational, as the name already says, the curl of the velocity field is 0. Okay? So the first one, look, this divergence, if something is divergence free, so if let me say like this, how should I say this? If I put it here, observation or fact, right? If divergence u, I put now the vector u, is greater than 0, then locally the flow is doing like this, right? That's why the name is divergence, right? If the flow locally is like this, the divergence being negative, it's actually locally, it looks like this. It's like a flow that's converging, right? So to a point in the sense that here, look, here it's intuitive, right? Here it's like the density it's expanding, it's maybe going down. Here the density is increasing because things are piling up. And another way to see this is from the divergence theorem. right? Divergence theorem, that if this is my region D, this is my curve C, right? This is the normal. And it's a balance of the flow on the border, right? So if this is zero, identically zero in the domain, right, the flow, the balance of flow, adding up the V over the border is zero, okay? We're going to come back to this later on, as you will see. Okay, so what else do I want to say here? Yes, okay, so now look at this. Now, we can basically use this fact here and let me play mysterious with you just for the fun of it, right? A little mysterious, that I can think of this as Cauchy-Riemann equations. Let's see how. Okay? Look, let me put a star here. Let's come over here. And let's write that in 2D, right? In 2D, right, the divergence of U being 0 is this. This is, let's say, well, okay, it's this one, right? Put it like that. And the other one is this one. Right? Just the definition. That's very easy, right? That's the definition. But now, look at this. This is the same as and this is the same as okay, so it's not quite Cauchy-Riemann. So not quite Cauchy-Riemann yet. But will be, as you will see. Okay? So it would be the Cauchy-Riemann, so it would be not quite Cauchy-Riemann, it would be the Cauchy-Riemann, let me say it in another way, for U and minus V. Right? But it looks artificial up to this point. But that's good news. Okay, that's good news. So it's not quite Cauchy-Riemann. Not quite Cauchy-Riemann. Let me put it like this, to be honest. In U and V. But let's put it this way. Could be for U and minus V. So to be seen. That's how we're going to prepare our modeling of complex variables with PDEs, which is Cauchy-Riemann, with fluids. Okay? So this comes only from fluids hypothesis. I haven't used complex variables yet in this blackboard. I introduced briefly in the other one, no complex variables here. Okay, so now it's the step where things are going to connect. So consider the following. So let's put it this way, let's introduce a complex valued potential phi of z, okay, which I am defining it to be phi of xy plus I C of x, y, okay, where phi is our velocity potential, uv equals grad phi. We already saw this in the water waves problem, okay? So let's introduce a complex variable potential. So because if I'm doing this in the fluids course and so on, I would do it more slowly with more details here. I want to just highlight aspects of complex variables with potential theory, with actually Laplace's equation and so on, okay? So this is a complex variable potential. Okay, Andrea, you did that. Well, the real part, we already know who this guy is. The imaginary part, we call it the stream function. You'll see why. This is called, you will see why. Excuse me, a stream function, which is the harmonic conjugate. At this point, harmonic conjugate, right? If this function is okay, is the harmonic conjugate of phi. If this capital phi works out well, okay, I'm sort of proposing you something. Let's see if it works, this proposition, okay? Okay, so let me compute d phi dz, okay, which is, I'll call this, and you'll see why, the complex velocity, okay, and you'll see what the complex velocity is. So I stop here because I have to look for things in my notes. There's more that I want to present, so that's why I stopped. So let me get back to the flow of the sentence so it works. I'm introducing to you a complex potential, which I claim it's going to be good, it's going to be helpful, right? And I'm going to start by putting the real part as our velocity potential we already know we're comfortable with. And the imaginary part is this guy, the harmonic conjugate, which actually is another sort of famous function. It's called the stream function. You'll see soon, maybe some of you might heard of it, you'll see it soon what it is. Okay, so if this guy is useful, and I know that the gradient of this guy is my velocity field, let me then compute the derivative of this guy to see how the derivative of this guy connects to my velocity field, right? Because we already saw from Cauchy-Riemann. So this I'm going to call the complex velocity. And I think this is a nice thing, is that even though it's like complex velocity, that means that there's a real part of the velocity and there's the imaginary part of the velocity. And you might think, oh, the imaginary part of the velocity, I'm going to forget about it. It's just like, right, the word imaginary makes us think it's a fantasy thing. No. They're both physical. They're both physical. The imaginary velocity and the real valued velocity, they're both physical. And you will see right now, okay? So if I differentiate this, right, the complex velocity, well, from what I saw from Cauchy-Riemann, this is the same as this. This is the same as this. Basically, I'm using from Cauchy-Riemann. I mean, from what led me to Cauchy-Riemann, right? Let me not put this. It's not Cauchy-Riemann. Right? From here, I take out Cauchy-Riemann. But what led me to Cauchy-Riemann was exactly the fact that I can take the derivative in the horizontal direction and in the vertical direction, that is, with a real valued increment and with an imaginary valued increment. That's all I'm saying, right? So I get this. All right. Now, this gives me the following. Yeah, let me write this one out. It's going to be, see this, phi y, okay. And this is equal, okay, I see what I'm so this is the same. I can write this like this, look. Okay, this is basically, this guy comes here, and this guy comes here. Okay. What do we learn? What do we learn from this? Look, playing with complex variables, what do I learn from this? I learn, look what I learned. This is U. This is V. So I learned, to start with, first thing, I learned that this is equal to U minus IV. So my complex velocity, and I like this, my complex velocity is basically U, that's the real part, which is the same as this, plus IV. And we also learn that U is equal to deep C dy, V is equal to minus deep C dx. So U is also equal, I can define it as the grad perp of the velocity of the stream function, right? I still have to show you why the name is stream function. We're going to see this next. Okay, so we learned two things, right? We learned, we learned this, and we learned this, right? I first learned that the complex velocity is U minus IV. And I also learned that, well, deep C dy is U, and deep C dx is equal to minus V. Okay, and now that I'm going to call the grad perp. It's like doing the perpendicular vector. Okay. Now, this first part is a very important part, is that my complex velocity is very physical. All I need to remember is that the real part of my complex velocity is my horizontal velocity. And the negative of the imaginary part is my vertical velocity. That's all. So it's very physical. The nice thing is that I can pile up two pieces of information, velocity horizontal, velocity vertical, into one guy, the complex potential. So I can work with the complex potential, and if I know my complex potential, I take the complex derivative, and I already have my two components of the velocity, right? Well, we kind of already did that, of putting two pieces of information inside one guy. That's the role of the potential. That's why this is called the complex potential. This was a velocity potential. So the good thing of the complex potential is that I'll be able to use properties of complex variables to get even more things out of it, of this modeling, okay? Okay, so that's my complex potential. All I have to remember is that of my complex velocity, this guy's the negative one. And now we understand this Cauchy-Riemann equation here with a minus V. Okay, because of this. So that kind of explains. So you see, the Cauchy-Riemann equation with the minus V is already guaranteeing to me that it is incompressible and that it is irrotational. Do you agree? See, Cauchy-Riemann with U and minus V is the same as incompressible and irrotational altogether in this packaging, the complex packaging. So kind of very elegant, very, very, very good. Okay, so let's continue with this, okay? If you have any questions, it's basically maybe terminology, the way I'm speaking a little fast, whatever, ask me questions, stop me, okay? Just like the other day you asked me what is spurious or whatever. It's something that's new, ask, right? Okay, so therefore, I can also write, let me write this here. Let me also write this, well, let me put in the other board. So we can also write this. And actually we're going to use that when we do that equation, that complicated equation I showed to you last class. The idea today in this class, let's see how I go, is to get as close as I can to the model. I think I'll get to the model, but who knows, right? I have to explain things. So this is the same, look, I mean, by definition now we know that this is this, which is the same as also this. Right? So if I want to write an equation for this appeared in our equation last time, which is the evolution of the interface, right? So this is basically, what is this? This is dx dt minus I dy dt, which is exactly this. So it's just notation, right? So it's just notation. Okay, what else? What else? What else? Okay, let me actually, let's check. So now, check level curve and which is called a streamline, and therefore this is called a stream function. So if I can parameterize it, let's put it like this. Minus a constant equal to 0. That's the same thing as the level line. Okay? And then I differentiate the total derivative of this guy with respect to the parameterization, I'll get this. Right? It's in the notes. I'm just skipping one calculation, very simple, which implies that the vector uv scalar vector is equal to 0, which means let's see if the picture speaks for itself. That's why I'm in silence. Let's see if the picture speaks for itself. So what am I saying is that if the flow, and this is usually true for flows that are stationary. A flow that's stationary, it means that it's time independent in the sense that the pattern doesn't change. So it's just like in terms of ODs, it's like when you have an autonomous OD. An autonomous OD, the vector field doesn't change, right? Like if we draw the vector field as arrows, they're always pointing in the same direction, right? That's an autonomous OD. The right-hand side of the OD, if it's dy dt, the right-hand side does not depend explicitly on t. So therefore, the vector field is fixed. And this is a little bit what's happening here. So the stream function, it's level curves. So stream function equal to a1, one constant, a2, another constant, a3, another constant. So it's this line. It is tangent. It is tangent to the velocity field. So in yellow, what I'm drawing here, I'm putting the vector sometimes like this, is the velocity field. Okay? Because dx dy is in the direction of the curve, and this is normal to the curve. Okay? So if these arrows don't change, right? We actually, these lines, the stream, so this is a streamline, this is another streamline, this is another streamline, which are level curves of the stream function. And the streamlines allows us to visualize the flow. Because if I put the particle here, it's going to go like this, another one's going to go like this, another one's going to go like that. Okay? So that's why it's called the stream function, because it has streamlines that allows us, to visualize the flow, the streaming of this fluid. Okay? Well, this guy is the imaginary part of our complex potential, and I just wanted to mention why it's called a stream function. Okay? Now let's see a little more of complex variables. Simple complex variables. Okay? So look at this. What does this remind you of complex variables? This integral, forgot to put this over some say closed curve. Simple closed curve, okay, something like this. What's the value of this integral? And there's a theorem behind this. So if phi, capital Phi, is analytic, right, because it has a derivative, the derivative also is an analytic, that neighborhood. In principle, there's nothing wrong coming from the derivative. So if this is an analytic function, let's assume that, okay, then from Cauchy-Goussat theorem, this is 0. So just very simple complex variables result. Okay? Well, boring, so on. Okay. Not so much. So look at this. This is, let me write this 0 in this ridiculous way, 0 plus I0. But because I want to break the integral in two, let's now take a physical, fluid dynamic kind of, could be other things too, could be electrodynamics, whatever, electrostatics. Sorry. So let's take now a physical interpretation of what this Cauchy-Goussat theorem is telling us. Okay? So look at this. This is the same as, let me skip one point, which is simple. And I'll leave it right. You check it. And let me copy here so I don't make mistakes. Okay, so what did I do? Very simple, right? What I just did is that I had u plus iv times dx plus I dy. And I get these two integrals. So that's why I wrote this ridiculous 0 plus I0, because this 0 goes for this guy, and this 0 goes for that guy. And then, I'm doing everything what I'm doing here is actually undergraduate vector calculus and complex variables up to this point, right? So it's very simple, but a nice interpretation. So the Cauchy-Goussat theorem for the velocity potential, or since I'm talking about its derivative, for the complex velocity, right? Gives me two pieces of information that looks like Green's theorem on the plane. Right? Looks like Green's theorem on the plane. Where this one, what is it telling me? Look how now we look things at complex variables, but then when we look like this, we can think as little vectors. This is like the inner product. Okay, this is like the inner product of uv with dx dy. Right, so in this direction here is a tangential. Let me do this better, sorry. I can write this like that, right? Like as an increment. If I have my parametrization, it's dx ds, dy ds. Okay, it doesn't matter. So this is in the tangential direction, and the other is normal. So look what these parts are saying. This part is saying that the circulation over the contour C, which is in the tangential direction, is 0. Circulation equals to 0, okay, in the tangential direction, this direction like this. So the net circulation is 0. So effectively, there's nothing rotating, right? And this one is the flow across C, because it's u, v, scalar, the normal vector. Look, dx minus dy. So there's 0 flow across the boundary. So this is related to circulation. That means that's related to having no rotational. Also, why? Because I'm doing this for an arbitrary contour C. I can make it small, I'm almost speaking Portuguese, small, bigger, and so on, right? So it's arbitrary. So I know that basically, so this is a nice interpretation of the Cauchy-Goursat theorem that we learned in complex variables here in fluids and connected with our PDEs and so on, that the real part tells me basically by using an arbitrary C, whatever I want, big or small, but like a simple closed curve, that there's no rotation and that there's no flow across the boundary, which means the density is effectively not changing, which means incompressibility. Cool, right? This complex variable is cool. So from the Cauchy-Goursat theorem. Okay. Now let's start getting things a little slightly more complicated. Not so much, but it really gets more complicated once we get to that singular integral, right? That sort of hairy object, but that we'll learn how to study it, how to do a stability analysis of that hairy, complicated equation I wrote there at the end of last class, right? Okay, let me give you now an example Okay, I'm going to give you an example of complex potential. There's quite a few here I'm skipping. If I do in the fluids course, I do other examples. I play with conformal mapping here. I'm not going to do that yet, right? Maybe I'll do conformal mapping maybe more towards the end of the course. I don't know. But at least now, let me give you one example only of a complex potential, because it's the one we need for the exercise we're going to do. Okay, that's why. So take this guy. What does this guy mean? Right? Look, a log. Okay, when we have the log in complex variables, we have sometimes to worry about the branch of the log, branch points. Let's not worry about this here, right? We might be taking the principal branch. The argument goes from 0 to 2 pi. Let's not worry about that. Let's just see what this guy tells us. Okay, this guy actually, the first thing, let me do one thing. This guy, this is a complex logarithm, okay? But let me see what the real and imaginary parts are. So let me write like this. Okay? So this is IA. A is a constant. Let's think of it as a positive constant. Okay? And look how things start connecting. Do you see a connection with PDEs here? Just writing this guy. A connection with what we already saw. We already talked about when we did when we started elliptic equations, that is Laplace's equation. Who is this guy here? Ln of r. Yes, very good. That's the Green's function for the 2D Laplacian. Okay? So this is the Green's function for the 2D Laplacian. This is the argument of z, which is also the arctangent. And actually we use this because it is, right? The harmonic could be the harmonic conjugate of this guy if we didn't have this guy here or whatever. Okay, and we have this imaginary part here in front. Why is that? Well, we'll see now. Because this is actually like this. This is phi. This is our stream function. And now, this is why this guy is good. Let me draw the level curves of the stream function. About a point, let's put about 0. Yeah, it's about point 0. So like this. Okay, so what I'm drawing in yellow, you can compute this, that u is going to be minus a over r sine theta, and v is going to be a over r cosine theta. So look how nice. This is very simple. I mean, in complex variables, we have to be careful about the branch. Let's not worry about this right now, because this is going to affect the theta. Let me take the principal branch, which is theta from 0 to pi. Okay? And look what this complex potential gives me. Let's see. I know some of you knows fluids. What is a name that I could give to this potential? I could give it a more physical name, right? The name of it's log of z, right? But I mean, a more physical name to this guy for those who know fluids. Or even if you don't know fluids, just using your imagination and thinking of what the flow is doing. This is a simplified model, whatever. Feel free to say it. It looks a little bit like, it has, good. I mean, it has a connection with magnetic fields and things like that. And there is an analogy between fluids and electrostatic and other things. For fluids, this is called a point vortex. Okay? In a very simplified way. So a vortex is something that's swirling, right? That we see if you have a sink, you fill it with water, and then you take out the tap, whatever, I forgot the name in English, the thing that covers the hole, and it starts swirling and going down. That actually forms something that's called a vortex tube, which is that eddy, that in Portuguese we call it turbilhão, right? Going like this. Redemoinho, right? Going like that. And if you collapse that scale of that thing to a line, to a curve, and if it's straight, it's a point vortex in the sense that from a fluid dynamics point of view, you can see something like this. Look, if this is our right? And everything is right-hand side, right? This is the flow in the box. Everything's rotating. Of course, it doesn't feel the edges of the box. So let's think of this in the very middle of a pool, a very big pool. Okay. You see this swirling. So this is the top view of this. The rotation, if you take the curl of a vector field, it comes out of the board, right, for 2D. So that's why I'm drawing it like this. And here's all the particles going around. And this is a macroscopic model of something that's swirling. If it's swirling in the pool, you see there is a little bit of a tube, a little bit of a hole, say here. We don't see it. It's a mathematical idealization of something that collapsed to a point. Okay? And look, the velocity field is actually going to be singular at r equal to 0. This is r. So the velocity field is going to be singular, but it's okay. This is still a good model for many things. Okay? Simplified and good model. So this is a point, this is called a point vortex because it has its support on a vortex. Okay? And these yellow curves are the streamlines, right? Streamlines. If I put a little piece of a floating device there, a little piece of styrofoam, isopor as we say in Portuguese, styrofoam, it will, of course in the ideal case, it will just be swirling around this point with this given speed. Okay? So this is our point vortex. And this is our complex potential for our point vortex. Okay, everybody good with that? And it looks things like also electromagnetism also. You have fields like that. Okay? Now, let's complicate this guy. And now I have time, I have half an hour, I think it's good. I'm going to very quickly complicate things without showing you, of course, much of the details, but just enough so that your intuition is okay, I hope. If I succeed, it will be my fault if it's not. And at the end, we're going to get a complicated object, which is going to be our singular integral. Okay? But I want to lead you towards that singular integral in a kind of intuitive way without seeing all the details and just give you the keynotes from complex variables, whatever we were using. Okay? So now a second example, let me call this example 1. So example 2 is getting this guy and complicating it more, like this. Oh, and I forgot to say, so A, which is this constant, is like the intensity of this swirling. Look, see, the bigger the A, the bigger the speed, the more it's rotating. Okay? So think of this as if I put, like this, if I put a point blender to mix a fluid, right? You know the blender, something to mix a fluid, right? So bzzz, put like it, bzzz, put a little bit of the noise just so you remember what I'm doing. Now, I'm going to put an infinite array of blenders. And you will see in a second why. All with the same strength. Doubly infinite. Okay? Put the sequence of blenders like this. Okay? Spaced by D. Okay? Things are going to get complicated, but mathematically we can handle it. So how does this look like? How does the streamlines of this look like? I'm going to show it to you. Well, look, right? I'm skipping some of the details. In the fluids course, we see this in more detail. But look, near any of these guys, it should look like this, right? So let me do this. So near any of these guys, let me stop here. The other ones are like this. Do you agree? So near the blender, near the vortex, everything is just swirling around. Okay? And we can show, it can be shown, that actually the streamlines are like this. Okay, it's kind of intuitive. Okay, it's kind of intuitive because let me try to share with you my intuition. near each vortex, right, things are a little bit like this. In the neighborhood, basically, I just see the swirling, I just see the effect of that guy. But then, if you move away, you start seeing the effect of the other guys, right? And at the end, these are the streamlines, complicated streamlines of this guy, which I'm still going to show you what the velocity, I'm still going to show you what the complex potential is, okay? But first I want to give you the intuition. Do these streamlines, let's see what these streamlines do before I ask you the question that was about this. So if I put something, a little piece of a floating thing here, it's going to go around that guy, right? If I put a little piece, a little boat here, it's going to go like this, feeling all these blenders, these vortices. Interesting enough, of course, in practice you can't do that because of perturbations and so on, but if you put a floating device here, so if you put a floating device here, what happens? Well, you did with your hand something that looks reasonable, so say it in words. No, it will not move. Yeah, it looks like it doesn't have, I'll get it. It looks like it does not have a definite speed. That's good. That's good. It's a good first attempt. But actually, it's going to be zero. I mean, theoretically speaking, okay. If you put some floating device here, then it's more of a non-defined speed because it doesn't move, but it's spinning like crazy. It's actually infinite, right? So it's basically it's not defined. Good, but here it's actually going to be zero. This is actually called because it's zero. It's actually called a stagnation point. Because something doesn't move. But it's actually, if you write the vector field for this, and then that's the next question I'm going to ask you. If you write the vector field for this, these points where the velocity is zero are basically critical points of the ODE associated to this, right? The critical point of an ODE is where the vector field is zero, right? So talking about ODEs, let me get some water, the chemicals say there, talking about ODEs, what does this remind you, this picture in terms of ODEs? Does that ring a bell? Does that remind you of something you've seen in ODEs? Maybe not, but I would say maybe yes. I would say yes. Okay, so let's think of this now in terms of ODEs, right? This is the streamlines for this fluid problem with infinitely many logarithms. And I'm still going to write, I got to be careful with the time, I'm okay. I'm going to write, I still have not written to you the potential using this guy. How do I get the one for this guy? Which I'll have to sum infinitely many logarithms. So we have to be careful. See where now it starts getting complicated. But first, this picture here of the flow, does it remind you of the phase space of some famous ODE? I mean, famous, well-known ODE. What does that remind you in terms of phase space, phase plane of an ODE? Does it sort of clicks in your mind something you've seen before? Well, let me say it. I'm seeing you getting anxious trying to say, this looks qualitatively, right? It's not, the curves are not the same. It looks qualitatively like the phase space of the pendulum. So this reminds us, so I'm going to put it like this, because then you can check. Of the pendulum, right? Of the pendulum. So this reminds us of the phase space of the pendulum. And let me show you qualitatively that it does. So this point here is the point at rest. Okay? This point here is an unstable stationary point, which is this one here. Okay? In between is the oscillatory, right, dynamics in here, in phase space. Phase space is position times velocity, right, for the pendulum. Here it's velocity, velocity. Okay, this is just velocity, u and v. And then, so in here, the pendulum is just doing that. It's doing a periodic motion, so it's doing a closed orbit in phase space. And so here is the unstable, here's a stable equilibrium. So you hit it a little bit, it goes like this. Here, it's the unstable equilibrium. You hit it a little bit, it starts moving, right? So if I push it a little bit, it goes into this orbit, okay? And you know, and if you give it very, very small time perturbation, it might go slowly and get to this guy, it takes infinite time. And what happens up here? Up here is if I give initial conditions, which is an initial position and an initial speed, that the initial speed is very high, so it goes like this. The pendulum, so it keeps on going to either one way or the other. Okay, so it reminds us, this is a curiosity. It's not that important, but it's curiosity. It reminds us the phase space for the pendulum. And then let me write to you, right, the complex potential for this guy. É por causa do 2π, exatamente. So the pi keeps on adding. Oh, yeah. Yeah, here it's just because the period it's invariant for this, right? And here because the angle keeps on adding, right? If I push it very hard, it keeps on just, right, adding the argument. So here's the potential for this guy. And actually, it's simple looking, but it's not that simple to deduce. Okay, so we went from this guy to this guy. How did we do that? It's really that non-trivial. So that part we're just going to tell you in words, and we're going to skip the details. Even in the fluids course, I basically, give you a little more details. But basically here, what's used, okay, what's important to use is, well, let me first say it, then I'll write it. Well, look, here, I'm going to add infinitely many of these guys by shifting this d, right? So this, I could write this like this, look. Z minus some z0, which in this case is 0, 0. Okay, but then I could write this guy plus z minus 0 plus this guy z minus d, which would be this guy. Then minus 2d, 3d, 4d, or the other way around. So I'm going to have an infinite sum, doubly infinite sum of guys like this. Looks crazy, right? But then you will see, I do this in the fluids course, I won't do this here, that you can manipulate things, okay? And when you sum logarithms, you usually can rewrite things as products, right? So this infinite sum will become an infinite product, and here comes a nice result. Let me erase this, which is the Weierstrass factorization theorem. Which for the sign tells us the following. Let me copy here. This actually, I wrote it afterwards in the notes. It's not in the notes that I send it to you, but it doesn't matter. So the Weierstrass factorization theorem tells us, oops, I forgot something here, that the sine of pi z, and I forgot something else, which is 1 over, sorry. I can fix it. Here we go. Okay. So the Weierstrass factorization theorem tells us that sine of pi z can be written like this, which is pi over z, infinite product of these guys. Here, going from here to here, we actually use it in the other way around. We basically have infinitely many logarithms that we're summing up, then suddenly, from the sum of infinitely many logarithms appears an infinite product of some guys. And the infinite products of these guys are this one. And then say, whoa, I know how to sum this infinite product from the Weierstrass. It's basically a sine, and that's where the sine comes in. So see, without seeing the details, you can believe this, right? So this guy, written in a simple way, comes out of a sophisticated theorem from this product, and then collapses infinitely many guys in this term. Okay? Good, I have some minutes to finish my modeling. So next class, maybe we can do then the linear stability analysis. So I think I'm going okay. Let's see. Okay, so let me repeat it here so that the blackboard, so that, right, we can have everything in the camera to be compared with. And this is for this guy. Yeah.
Tem alguma situação física com essa característica dos vórtices, né, não no pêndulo, por exemplo, mas em fluido dinamicamente?
So you're asking so that people know what you're asking. Is there like a physical case where you have these infinitely many spaced vortices like this, right? Let me say, not quite. Let me wait. I think I'm going to answer your question right now. Okay? So you will see what I'm going to do. Okay? This is like an intermediate step. And I'll answer your question. Ask that question to me again if I don't answer it in two ways. I got to answer it in two ways. I'm going to start answering the first way, okay? So please remind me. Okay, so this guy now, I'm going to do one thing. I'm going now to do this. I'm going to get some window. Let me think of this one. Okay? And I'm going to spread this vorticity uniformly as a density over this interval here. Okay, so that at the end I have the same amount of vorticity. So if I do that, okay, so this is the discrete case. And now we can do a continuous case, or a continuous case where it's going to look like this. So I'm skipping some details, of course, but I think that you will understand. Okay, where here I am, so summing, say this is an interval 0 to 2 pi. Okay, so think of this, like I have two, as we sometimes in engineering you think, you have like a lumped mass, so a concentrated mass, or a concentrated density of vorticity here and here, and I'm going to spread this vorticity over this interval, not using this guy. So this guy, so basically, so that the vorticity, basically, instead of being A at each point, it's A ds. And when I integrate it, it becomes with a 2 pi. That's why I divide it with 2 pi. So this is now is this guy along that thing, okay, with a sort of a constant density. So this is like this. Let me write like that. Sorry. Let me see if I explain. This looks a little bit like I think sometimes in physics you would write. But I'll come back to what I did. This is, I'm summing over an interval 0 to pi, infinitesimal vortices of strength AdS times the potential of each of these guys. And each of these vortices are centered at this point S that varies from 0 to 2 pi. So it's a continuous distribution instead of a discrete one. Okay? And now comes my answer, my first answer to the question Manuel asked me, is that this, okay, this guy represented this. Look. Okay? And you know what this represents? And that's my first answer to you. So, now let me free my hands so I can help you better, is that, look at this. As I'm piling these guys together, it's like I'm doing this. Okay, let me do a picture. I think it's going to be good. So you see, as I'm sort of piling these guys together and going to a continuous limit, at the end, we do not see this microstructure. We just see the outside structure, which is exactly this. We don't see anymore what's the details inside. Okay? So therefore, this guy here, look, phi of z, what have we achieved? We have a complex valued potential, that is a function, complex valued function, that has a kind of non-trivial interpretation. So it's an integral representation, right? It's a function of z in this integral form, right? Which, if z is a point here, or z is a point here, this is an analytic function. Nothing, it's crazy looking, but nothing bad about it. Okay? And what this function does, it represents this function. So let me write like this. First answer, well, this function represents a shear flow. Right? Shear flows means like this. One, like when I cut a piece of paper, shear mean cutting. In Portuguese, it's cisalhante. So it's like cutting something. So it's this relative thing. So it has this jump. So this is an integral formula, kind of a crazy integral formula that represents this flow that has a jump. So now, remember, I mentioned to you that interesting things are things with singularities. So there's got to be some singularity in here, which I'll mention to you, maybe not today, I don't know how else I'm going to run, right? That represents this jump in flow. So let me get my water and ask you, what is the vorticity? What is the curl of this flow? That's basically, the curl is just calculus, and I've already given, I mean, I'm being hard on you, but I've given the answer in this course before, but I'm being hard, okay? Look at this. So the vorticity for 2D flows is this, okay? So what is the vorticity what is the vorticity of this flow? Let me start helping you. The vorticity, let me call this Z1 or Z2, I think, because I'm going to call 2 up and Z down. So this, you can think of this as two fluids. Fluid 2, fluid 1, that do not mix under this shear flow, okay? So what is the vorticity at Z2? So at Z2, the vorticity is omega. Omega is 0. Okay? At Z1, omega is also 0. Why? Very simple. Because over here, V is what? 0. Okay? Over here, V is 0 and U is constant. Same thing down here. So V is 0, U is constant, they're both 0. Right? The derivative of a constant is 0. But now, look at this. Let me do a velocity profile here. The velocity profile here, if I look in the y direction, the velocity profile here is that it's negative here, and then it's positive here. This is for u, the graph of u. U is negative here, and it's positive here. So basically, the graph of u, in terms of y, is like this. No, y positive, it's negative, so it's like this. Okay? So I'm going to ask you again the question. What is the vorticity at y equal to 0? Because this is for y greater than 0. This is for y smaller than 0. And what is the vorticity for y equal to 0? 1 second. What is the answer? Delta Dirac. Because this is a Heaviside function. Very good. So this is delta Dirac. So you see? So we have a singular vorticity distribution here. A singular, if we didn't think about fluids, we have a singular distribution. We have singular derivative in our data, in our information, right? Because I'm starting with this flow, right? And you can actually show that this flow is the solution of the equations. It's right? It's time independent. It'll just stay like this forever. I will show you this next time. Actually, one way to show this is using a very nice theorem from complex variables that not always is taught, which is the Plamelli theorem. Okay? But you can see now that this integral representation here, right, has some properties yet to be verified. First hypothesis is not difficult, is that this is a complex valued function, and phi, so facts, so phi is analytic in 2 and 1, meaning not the interface. This is the interface. But away from the interface, it's analytic. And you can basically differentiate this in z, but you'll see. Okay? So if z is away from the interface. So if it's away from the interface, this crazy guy here guarantees to me, without me having to check, see, this guy guarantees that I have an incompressible irrotational flow upstairs and downstairs. Now the difficulty, and that's what I'll leave to next time, is that what happens when I take z and I let it approach the interface from above, and I take z and I let it approach the interface from below, since we just saw that the interface has some singularity, right? The first derivative, which is the vorticity, the first derivative blows up as a delta Dirac delta function. So you see now from the PDE's point of view, this complex variables object has good properties and properties to be checked. First, it satisfies Laplace's equation on top, satisfies Laplace's equation on the bottom. You agree? Because it's an analytic function, so. But its first derivative blows up because the vorticity blows up, but blows up in a nice way, in a Dirac fashion, that's why we call this the interface. And maybe I should finish here. The interface is called a vortex sheet, meaning in this case a line. A sheet, if I sit like this, coming to you, okay? So it's like a plane where the vorticity distribution is singular there and zero outside, just like a Dirac function. So this is called a vortex sheet. And a vortex sheet is good. Oh, I have to say one more thing, or else I'll be cheating. I have a minute. Is a good modeling object for this shear flow. And where would I have a discrete case like this? Okay, so there's a flow about the cylinder like this, that you put the speed u here, okay? And the flow usually is like this, right? It goes around the cylinder, okay? But if you increase this speed very much, and you can see this in rivers sometimes, you have a pair of vortices here. This does this. And these vortices at one point then, if you increase more the flow, they are released. And you get this. And you get a vortex here, 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 which is called the von Karman vortex street. And this is a doubly discrete. So this guy is a first exercise to get this guy. Okay, so these are vortexes that go like this. They're sort of staggered. One here. I'm not drawing very well. And this is what you see, for example, behind a ship. So if you have a ship and you see the wake of a ship. Okay, if you see a ship moving this way, behind the wake of a ship, you see a pattern like this, okay, or airplane going through a cloud. And these are these point vortices, which are exactly this guy with another one like this. That's what I mean by staggered. Okay, so good, you asked me a question. That's the answer for the physical modeling of that. So let's finish here, and I'll come back to this complicated integral next week on Monday. Okay, but this is a good review of complex variables, and we already got very quickly something complicated.